Here's our question. We're going to find how much the vapor pressure gets changed compared to pure water for both of these two solutions. And we are also given this piece of information. So I guess we're assuming this is happening at 20 degrees. Here I propose step 1 should be to find the vapor pressure with sucrose. And here's where to think about Raoult's law. The pressure in some solution is the vapor pressure of the pure solvent times the mole fraction of the solvent. So in this case, the solvent's water. A common mistake might be to use the mole fraction of the solute, sucrose, but no. It's the mole fraction of water, which is just the moles of water in the solution divided by the total moles. So it's going to be pretty close to 1, because most of the solution is water. And you might think we're stuck here because the question doesn't tell us the total moles of water or the total moles in the solution. So we have to use our brains a bit. We are told that it's 2.3 molal of sucrose. And that means that there's 2.3 moles of sucrose per 1 kilogram of solvent, which is 1,000 grams of water. So here's a trick we might do. Let's just pretend we have an amount of solution that has exactly 1,000 grams of water in it, and therefore exactly 2.3 moles of sucrose. Now we have one part of the puzzle, 2.3 moles of sucrose, which is, half of the story for our total moles. Now we just have to find the moles of water, and we can use this to do that. In this imaginary quantity of solution with 2.3 moles of sucrose, we have 1,000 grams of water. All we need to do is convert that 1,000 grams to moles. So divide by the molar mass, right? And what is the molar mass of water? It's 16 for oxygen plus 2 for the hydrogens, which is about 18. And that gives us a very pretty number, a beautiful number of 55.5 moles. So now we can go back up and begin to find our mole fraction. We can plug in that 55.5 here for the water moles, and then the total moles are all that water plus the sucrose. And there's our mole fraction. I told you it would be mostly water. And now that we have that mole fraction x, we can continue to move backwards and plug that in here. Now that's the actual vapor pressure of the sucrose solution, but we were asked about the vapor pressure lowering. So that would be the difference between pure water's vapor pressure and the sucrose solution's vapor pressure. And this right here is the amount that it changed, or the amount that it lowered. Now let's think about the sodium chloride solution. How are things different for this solution? There's an overall higher concentration of overall solute, twice as high, because you get 2.3 molar sodium plus, you get 2.3 molar chloride. So when we calculate the mole fraction of water, we have the same 55.5 moles of water divided by the total moles, which are a little bit more. 2 times 2.3. So you overall have a lower mole fraction of water because you have twice as many solute particles. So to find the actual vapor pressure of the sodium chloride solution, we take the vapor pressure of pure water, multiply it by that lower mole fraction of water, and get a lower value than we did for the sucrose. And there is your change. This is the lowering. And yeah, for you can't just double it. No, for those of you who are trying to do a little trick and get away without doing the math, this is where it pays off to actually do the math. Doubling the molality of total solute does not quite actually double the vapor pressure lowering.